Welcome back, everyone. First of all, small announcements. Someone dropped an HTC phone in this room last session. So if anyone is aware of who that belongs to or hear about anyone having lost a phone, it will be out in the reception desk for the owner to pick up. And we're moving on to our next session here, which will be Dr. Chris Doran from Cambridge University. First-time speaker at HaskellX, and we'll be talking about geometric algebra in Haskell. So please give them a warm round of applause.
Well, thank you, Frederick. So I work mostly at ARM Research, and I'm part-time at Cambridge University. This is a talk on research that I've been involved in for many, many years as an academic and sort of a spare time hobby. I don't usually give these talks with corporate branding, but something very, very exciting has happened at ARM over summer. We've rebranded for the first time in 25 years. We are now a lowercase company. So I thought, thank you. You'll be glad to know the person responsible for that got a massive promotion as well. Though we're not always completely lowercase now. We're a little bit unsure, but we're no longer capital. So the way I like to think of it is we no longer stand for anything. I'm also a part-time fellow at Cambridge University. Pleased to say I don't think their branding's changed for over 800 years. So I wanted to try and do something very, very different here. This is not going to be a talk where you're going to learn anything about Haskell. I saw on the program this was down as a beginner talk. Beginner refers very much to the speaker as well as the audience. I'm very much an amateur Haskell. I've been playing around with it for many years, but I wanted to talk about something that sort of really struck me over the years of playing with it. The way it fits naturally with the mathematical language I'm going to talk about, geometric algebra, seems very natural. There's something quite profound about the way they fit together, and it's more than just Haskell's a good math language for maths because it's written by mathematicians, it's got mathematical structures. There's something a bit more in that the right structure that you need to instantiate geometric algebra manipulations is always just there. It's always there in Haskell. You're never fighting for anything. Now, I often give lecture courses on geometric algebra. I've just started another one in Cambridge last week, and I'll put some references up at the end if you want to sort of download the slides from that. It usually takes a good 8 lectures to get anywhere into the subject. That's a cut-down version of a 16-lecture course I used to give, which is based on a cut-down version of a book I wrote with some colleagues many years ago. And during this 8-lecture course, I usually try to throw in a lecture where I explain why I think this map between geometric algebra and Haskell is so interesting. So I'm trying to motivate people interested in geometric algebra to learn about functional programming. It usually goes very, very badly. So I thought I'd try to do the reverse here and motivate geometric algebra through people interested in Haskell and see if I have any better success. At the back of this is the idea that geometric algebra is a form of strong typing for geometry. So what I mean by that is when you start working with geometric objects like vectors and so on, when you do it by hand in geometric algebra, you don't just work with a list of 3 numbers and say that's a vector. If you've been taught tensor algebra, you may say, no, I'm quite happy with that top notion. But if you're a geometric algebra person, you say, no, it's meaningless. It's just 3 numbers. Until you tell me how they multiply together some frame vectors, I haven't actually got anything. And what we do, this sort of primitive way we actually think about vectors is they're just abstract elements of some vector space with some rules attached to them. And we can attach pictures to these rules. So we want our addition to be commutative, and we want it to be associative. And we can draw pictures for why that would make sense. But in the end, we define an algebra, and then we decide how we're going to use that to represent geometric artifacts. Now, this talk, I will get to some code soon, but there's a little bit of maths I need to do first. Hopefully nothing particularly challenging. And one of the things I usually try to stress in the geometric algebra course is that there's this sort of perception out there that you've got complex numbers, then quaternions, they're quite abstract, and geometric algebra is somewhere sort of off in the distance, it's highly abstract. But it's not. It's a really simple, concrete thing to understand, and I hope, by giving you some Haskell tools to play around with it, you'll be able to take that away and try it out for yourself and convince yourself this is true. The origin of geometric algebra goes back to the 19th century when mathematicians like Hamilton and Clifford and Grassmann were wrestling with this question of how do you multiply together two vectors. Everyone had seen how complex numbers had revolutionized understanding of two-dimensional geometry. They have a natural product. People wanted to extend that to 3D and higher dimensions. And the sort of concepts that were floating around at the time were people already knew about the inner product. This is defined as the inner product between two vectors is the magnitude of one times the magnitude of the other times the cosine of the angle between them, and it has a component form that you can derive. So this is derived, this is kind of the definition. And there was also this notion of a cross product, which I think most people are familiar with. It is actually anti-commutative, and it returns a new vector, though I could put that in inverted quotes because it's not quite a vector, perpendicular to the plane defined by the two input vectors a and b, with magnitude ab sine theta, and such that the a, b, and n form a right-handed set, and the right-handedness is built into the definition. This is the actual definition of the cross product. The algebraic form you've given with an epsilon tensor or other ways of calculating it is all derived, but this is how you define it geometrically. So we have these objects, but on their own, they're not particularly useful. They don't seem to give you what you get from complex numbers in 2D. Though the prevailing wisdom at the end of the 19th, early 20th century was this is essentially all you need. Because pre-special relativity, everything was three-dimensional. You just needed a dot product and cross product. You could kind of get by without learning anything else. Now, various people had a go at trying to generalize complex numbers to higher dimensions, but the person who succeeded was this guy. You can just see up on the top right there, William Clifford. He was a mostly Cambridge mathematician, spent some time at UCL. And he died, unfortunately, he died tragically young. Though you wouldn't believe it from that picture of him, he was only 33 when he died. Sporting, doesn't come out very well though, but Victorian analogue of a hipster beard. Now, he defined a new type of product. He called it the geometric product. Since then, it's often become known as the Clifford product, but I actually kind of prefer the name geometric product. It gives it sort of more, makes it seem more fundamental. And his idea is that the product of two vectors should be a mixed quantity, a sum of a scalar, the a dot b term that we all know, and a new thing that represents a plane. Now, this is the point where a lot of physicists, indeed professors, have sort of walked out of the room saying, this is nonsense, you can't do this, you can't add two different things together. But you can. This is no different from adding together the real and imaginary part of a complex number. We write down 1 plus I, we know what it means, we've got a 1 and an I. If you were a really pedantic mathematician, you'd put a circle around the cross there and say it's a directed sum. But nobody does that for complex numbers, doesn't add anything at all, so we just use the same notation. And this is our defining property of the algebra. Now, there's a couple of bits of derivation we can do from this. A couple of other things we want to build into the axioms. First of all, we're going to make the geometric product distributive over addition and associative. It's our product. We can define it how we like, so we're going to give it some sensible rules to make it easy to work with. The other thing that follows, essentially, or is a sort of primitive axiom, is that the square of any vector is a scalar. Kind of comes back to here, because the dot part has got to be symmetric and the wedge part is anti-symmetric. So something multiplied by itself only has a dot part, so it's a scalar. If you then just take the sum a plus b and expand out using the associativity and distributivity rules, you can also see that because the left-hand side is scalar, a squared and b squared are scalar, that the symmetric part of this product is also guaranteed to be a scalar. So we define the inner product as the symmetric part of the product's two vectors, and the outer product is then the anti-symmetric part. And everything's built up from the geometric products. So it's essentially one product, but we can pick off different bits of it and give them different symbols. And just to see how this works in 2D, which is pretty much all we need to do to understand what's going on, let's just introduce two base vectors, E1 and E2, and we'll assert that they're orthogonal to each other and that they are unips. They're orthonormal vectors. E1 squared is 1, E2 squared is 1, and E1 dot E2 is 0. From this, we can see the two basic properties of the geometric products. Kind of everything else is built up from this. Parallel vectors commute with each other. So E1 times E1 has to be symmetric. You can swap the E1s past each other quite happily. You just get the number 1 anyway. The wedge part drops out. But orthogonal vectors anti-commute. So this is the key property. E1 times E2 breaks down into E1 dot E2 and E1 wedge E2. E1 dot E2 is 0 because they're orthogonal. E1 wedge E2 is minus E2 wedge E1 because of the anti-symmetry of the wedge product. And I can get rid of the wedge and replace it with the geometric product because there's no dot term to bother about. So I get E1 E2 is minus E2 E1. So everything, when you're multiplying these things together, is just a question of counting how many times these vectors swap past each other. And this is the whole key property. The geometric product breaks down into something that tells you how much two vectors are parallel to each other and how much they're perpendicular to each other. And in that way, they capture all of the information about the relationship between two vectors, and it means that the product is actually invertible as well, something you don't get with a dot and cross product. Now, this gives us something that is either sort of blindingly obvious or quite surprising. For me, this is really surprising. This is the bit where, in the very first lecture on this subject, I sort of sat up and started paying attention. We've just defined some fairly sensible rules for how you might want to construct a product for vectors. And we've come up with this new thing, E1, E2, and typically it gets called a bivector. It sort of represents a plane somehow. But it has its own algebraic properties that it inherits from the axioms that we've just established. So we can look at what happens when you square it. You can look at what happens when you take E1 wedge E2 and multiply it by itself. So we get rid of the wedge. We don't need it. We get E1 E2 times E1 E2. We can get rid of the brackets because everything's associative. So we get E1 E2 E1 E2. We can swap the middle two vectors past each other. Brings in a minus sign because they anti-commute. Then we get E1 squared is 1 and E2 squared is 1. So the overall sign is minus 1. So we've invented, from pure geometry, we've invented something that squares to minus 1. And actually, we've essentially invented complex numbers. Now, I sometimes sort of present this, and people get upset, say, well, we already know about complex numbers. Part of the point here is that we know about complex numbers as roots of quadratic equations for purely historical accident. People discovered complex numbers in that context first, and discovered them in this geometric context later. Maths is full of this. Maths is full of this idea that the historical order at which things were invented is the correct order, and that's how stuff should be taught. In fact, this is a much more intuitive way of understanding complex numbers because it's all geometric from the ground up. And if this had been discovered first, which could easily happen, it's nothing desperately more complicated, we would teach complex numbers a completely different way. And somewhere in around sort of lecture 5 or 6, there'll be a little aside that says, oh, and by the way, they solve all quadratic equations. And the point is that there are the design principles here, which the mathematical community rarely think about. But the programming community thinks about these things very, very deeply. They all care about the right way to design a language. And particularly, the functional programming community really, really care about this sort of stuff. So that's the algebra that we want to instantiate in Haskell. And that means that we want to find a type for the various objects there, and a product for how we multiply them together, and then a sort of simple library that we can build up. And I've written sort of geometric algebra libraries many, many times in many, many different languages, but Haskell has been by far the cleanest. Now, that might be because it was the last one I did and I've just got better at it. But I'm pretty sure, I think there's far more to it than that. So first thing we need is a way of encoding these vectors, bivectors, and so on. And you saw that they are essentially just products of orthogonal vectors. So there's a natural way of representing this with just a straightforward binary representation. So we're going to actually just declare the scalars are just essentially the empty set, or 0. Actually, we use them interchangeably. The vector E1 just has a 1 in the 1 component, and E2 is a 0 and a 1. And E1, E2 says, now I've got both of these present, so we represent that as 1, 1. So very natural, essentially a reverse binary representation, and that captures all of the basis blades that you can form. And this is our complete set in 2D, and you can see just how this goes easily in 3D, where we have 3 basis vectors, E1, E2, and E3, 3 potential blades, E1, E2, E1, E3, and E2, E3, so 3 planes, that's what we get in 3 dimensions, and a final thing, which we often call a trivector, which has all 3 of them, and it represents a volume in 3-dimensional space. I've put some extra zeros in just to make it a bit more readable. So you can see how attached to each component, I can have one of these objects that will tell me exactly what the thing is. So that's what I mean about strong typing. I don't want to work with just a list of 3 numbers. I want to know that the numbers are the coefficients of E1, E2, E3, and not coefficients of a quaternion or an axial vector or some other thing. At the very least, you'll capture an awful lot of geometry bugs in your code. And one of the things that sort of set me thinking about this was the company I ran before worked at ARM, where we did graphics for video games. The number of times that people would just sit there trying stuff out, trying to figure out whether they're in a left-handed or right-handed coordinate system and whether rotations would rotate the right way or the wrong way. It was essentially trial and error because they just had sets numbers rather than something more strongly typed. So we want to implement this in Haskell. It's going to be a little bit heavyweight if I carry around a linked list of integers, zeros, and ones everywhere. So rather than actually carry around the list, I will represent a blade with the binary number that you get just from the reversing the order here. So we'll define a new type, multivector, with a constructor, MV, and the type is just a list of pairs where n is the integer representation for this thing, and a is whatever the value is. And I've actually set it up so it's polymorphic, so and has implemented an abstract data type, so you don't actually expose a constructor, you just expose a function that constructs a multivector, and it can take in any type of number, and you can define a geometric algebra over sort of essentially any number field inside Haskell. It's probably unnecessarily heavyweight doing all the abstract data typing and polymorphism, but it's quite fun to play around with. And it works nice and easily. The only thing I have to be slightly careful with here is that essentially you need 2 constructors for whether I want the blades to be represented by an integer or by an int or a long integer. That's because I might want to be looking at rotations in some 40-dimensional space, and I want to encode things, and I will need a bigger integer to encode the size of blades there. So this is all quite natural, works very easily. The actual constructor itself is based on a function that essentially has to read in how you would type the blades, and I'll show you how that works. So that's just an IO function. and then they're all sorted, and they're sorted by sort of scalar, then the vectors, and the bivectors. It's easier, gives you some little optimizations later on if you can assume all the way through that your list is sorted. But you see, one of the first things that drops out here is that you are naturally, in Haskell, led to representation of a multivector as a list, which is exactly how you do it in practice. This is, say, much easier than trying to implement it as matrices, which are all, or arrays or something like that, which are slightly more clunky to deal with. I want to be a list because the list is a nice, sparse representation of my object. In a lot of the C++ instantiations, for example, you define an 8-component array, and you'd set most of them to 0. So if you were dealing with a vector, you'd have zeros in the first and the fifth, sixth, seventh, and eighth slot, which is a really clunky way of doing it, very inelegant. This is very nice and elegant, works well. Now we need a way to do the product. So essentially doing this product is taking the blade components and multiplying them together and shuffling them around so that if there's common vectors in both, they move to each other and then they annihilate each other. So for example, E1, E2 times E2, E3 is E1, E3, so I can take the brackets out, I get E1, E2, E2, E3, and then the E2 squared 1 collapses out of this product. If any one of you have ever actually got to the point of doing some fermionic quantum mechanics, it's exactly the same algebra as creation and annihilation operators. Except when you see it like this, you see just how simple it is. And this actually is just an XOR. It's essentially binary XOR. And if I get time, I'll talk about this a little bit at the end. There are some fairly obvious optimizations that we'd really like to get into this, but if we could work with this, the binary representation, this would just be a straightforward XOR. The only thing we have to be careful with is we can't use a standard zip with operation because we've got to make sure that the zip is done over the longer of the blades, not the shorter of the blades, so we don't throw some stuff away. So very easy to do. I think that there's almost a library function that does this. But anyway, it's one line to write your own. So that tells you what the resultant blade will be. The final thing is we've got to get the sign right. And the sign comes from counting the number of swaps that we make. So here, for example, on the left, we've got something that represents E1, E3, E4. And on the right, we've got something that represents E1, E2, E4. And we're going to multiply them together. And you can sort of do it in your head. You take the brackets out. The E4 goes past the 1 and the 2, so past the first two. 2 flips, so you come back to yourself. And then the E4s hits the final E4 and they annihilate each other. You're then left with E1, E3, E1, E2. The 3 now has to go past the 2 in front of it to get to its natural slot at the end. 2 more swaps, and then it just sits there as an E3. And then you've got nothing here to swap by. And then the final one, the first one here, is then up against its thing and its pair, and they just annihilate down. So you've got 4 swaps. So the total here will be a plus sign overall. Okay. So that's easy to do. I've implemented lots of different ways, but actually I think the really neat way is to take the second blade, second representation, do a consecutive sum over it, because that essentially counts the number of swaps as you go past each one. Take your first blade, drop the first term in it, and then zip them together with a product, and that gives out the final number you want, and then you just return it mod 2. So this is the blade product. Now, I'm sure you get this all the time in Haskell lectures. I've written this many, many times, many languages. I've never, ever got it close to being a one-line operation. But it just drops out here. Very, very simple. Even the extra bits you need, like the fact that I need to pad out with some zeros, is easy because I can just use laziness and an infinite list of zeros and just add them on the end. Incredibly simple to do. And as experienced Haskellers, very easy to understand. You can see exactly what's going on. And now we've got the blade product. The next thing we need to do is lift this to multivectors. But a multivector is just a big list of blades. If I want to multiply together two multivectors, all I do is I take all the blades from the first list, all the blades from the second list, multiply them together to form an object res, and then sort it. So you have to sort it because some of the products will give you things that are in a different sequence. And when you sort them together, you also have to simplify because you may get an E1 occurring twice with different coefficients. You add up the coefficients. So again, utterly simple, trivial stuff. And once you've written a couple of support functions here, you can do the entire geometric product in basically one line. Extremely simple. And the last thing you can do, this is the thing I really wanted to do in Haskell, is add it to the num class. Just for the really childish reason that I really like to be able to write A star B in my code. I don't want to have to write geometric product of A and B or anything like that. And it means that the code you write is a one-to-one comparison to what you write down on the page as a theoretician. You don't lose anything from converting, other than the fact that your labels have got to change a bit. And it's so much cleaner and easier to understand this than trying to do the same in an object-oriented language where you have to have some operator that's attached to the first one that acts on the second one. It just looks wrong, it breaks associativity, and so on. So this is all really nice, simple, elegant, easy to do. So I'll just show you what a sort of typical session would look like. We'll call up that and that. So this is just some test script. So let's say we're working in 3D. You can see the constructor commands there. So you write down the coefficient, and you write the blade as a string. And because it gets a bit tedious writing these, it's often easier just to sort of give them an extra symbol. So E1 here is just a vector. Hope that's visible. E2 is a vector. And I can take E12, multiply with itself. I get -1. I can do other interesting things. I can take E1 and multiply it by E12, and I get E2. Okay? And I can do the same thing to E2, and I get -E1. And that tells you that multiplying on the right by E12, this blade, has rotated through 90 degrees. That's what I mean about this essentially being complex numbers in 2D. We can also lift up to 3D. I've got three objects now. I've got E12. I've got an E13, so I can multiply E12 times E13. And I get E2, E3, E23, and so on. And if I complete that algebra, I find that if I set I to E2, E3, j to minus E3, E1, and k to minus E1, E2, these bivectors satisfy this algebra. I squared j squared equals k squared ijk is -1. So in 3D, you get quaternions for free. You've just discovered them. They're just there, sitting in the algebra. That's Hamilton who discovered the quaternions. Quaternions are the correct way to do rotations in 3D. If you've ever sort of looked at physics engines in sort of game engines, all of the rotational dynamics is done with quaternions because it's much easier. So I've defined one here. RTR is a unit quaternion, sort of 1 over root 2 plus minus 1 over root 2 E1, E2. And a little function I need is the reverse of that, which essentially flips the sign of the bivector bits, just changes that from a minus to a plus. And I can do things like that rotor times E1 times the reverse of it. And I get E2, to engineering error, at least. Anyway. I can put an E2 in there. And I get back -E1, so it's rotated through 90 degrees. And if I put E3 in there, it stays the same. So E3 is the axis. So this rotor represents rotations very, very naturally in 3 dimensions. One other thing you can see very quickly is in this 3D algebra, I've got an I, a trivector. And that has another interesting property. If I take E1, 2, 3, it looks like, where's it gone? I1, 2, 3. Oh, wow, thank you. It was I3. That's right. I had a good reason for doing it at the time, and I can't remember what it was now. Yeah, I3. If I take I3 and multiply it by a vector, E1, I get E2, E3. I get the plane back perpendicular to that vector. And if I multiply a plane by I3, I get a vector back again, which is all very neat. And I3 also has the property that it squares to -1. It's another imaginary type object. And I can summarize my 3D algebra like this. The product of two things is a scalar part, the delta function, and a bivector part, which I can actually dualize back. Now, if you remember that the I here, the I3, squares to -1, just with a little bit of change of notation, I can do this. I'll put hats on them, because that's what quantum mechanical people do. They have hats on everything. But the algebra is exactly the same. You have discovered the Pauli algebra of quantum mechanics, but only just through pure geometry. We haven't said anything about quantum mechanics anywhere in any of this. So you get a lot of quantum mechanical concepts come for free. Just coming back to this strong typing point, our 3D bases consist of 8 objects: a scalar, 3 vectors, 3 bivectors, and a trivector. And if you work with GA the way I think it should be done, you will always know exactly where you're working, what you're working with. This is particularly important in distinguishing between vectors and planes. So if any of you sat through lectures on vector geometry as undergraduates, at some point your lecturer will have mumbled about the difference between polar vectors and axial vectors, and then sort of quickly moved on because it doesn't really seem to make much sense. Axial vectors are a mistake. They should never have been in physics. Axial vectors are planes. They're bivectors. And if we'd never bothered with trying to represent with their dual concept, things would be a lot easier. So things like angular momentum, the magnetic field, and so on, they're bivectors. They are actually planes. It's just that the language that you had was insufficient to express that. And with this duality thing, you can also recover the cross products. You take the plane from A and B, the wedge product, multiply it by -side, gets you back a vector. It's not a good thing to do because it only exists in 3D. You're better off just working with the wedge. So I want to make a couple more comments. Nearly out of time. Most geometric algebra expressions tend to involve, 5 minutes, good, a bunch of products and then a projection onto some graded element at the end. So the only other thing you kind of need to get everything you want is a projection by grade, which is a nice, easy thing. Again, you just filter out the terms of the correct grade. And this is where laziness is a big help, because if I only want the scalar part of the product, A times B, I can just write down, right, just give me the AB part. And you can go through and check that by doing this, without any change to the code, laziness will just only bother calculating the terms with grade 0. So that's a nice little optimization that comes along for free. and that works. If you're trying to do this with sort of templated C++ stuff, you'd have to just, essentially, you go to Maple, it tells you what the thing is, the grade 0 part is, you take a big expression, you paste it into your code, and you sort of hope for the best. Another thing we get for free, just going back to this example in 2D, I've defined a little function here. It's a linear function that takes in a vector and spits out a vector. So I can let ff act on E1, and I get 1 lot of E1 and 2 E2, and I can let it act on E2, and I get 3 E1 and 4 E2. I can now define something which has the slightly clunky name of an automorphism, but it essentially just lifts this action to higher grade objects. I can take the function ff, and I can apply it to E1, 2. And I get -2 E12. The only code required to do that says when you take something that's acting on two vectors, you let it act on one and wedge it with the result of acting on the other. So I can now just declare this automorphism as a function, and it turns out to give me -2. Anyone guess what the -2 is there? It's the determinant, exactly. You've got the determinant for free. And this result actually works in any dimension, any signature. Once you've defined the automorphism, all of that linear algebra comes for free. And as a result, actually goes back to Grassmann, who failed to achieve the full hipster beard in the 19th century. A couple of extra little fiddly details here. It turns out in practice that it's actually really useful to have vectors of positive and negative signature because we want to do special relativity. There's some interesting stuff with conformal geometry that also needs mixed signature. So in the actual code I've got, I interleave positive and negative signature vectors to make things a little bit more general. It's probably not optimal, but it's good for sort of experimentation. But what I've done so far is not optimized correctly. I think using this sort of parametric polymorphism is going to fight against some optimizations. I'd like to get memoization in there, but I'm particularly keen to work with people who are interested in this, who can help me write some more highly optimized libraries for some of the more specific cases. And just to finish up, I've shown you how in geometric algebra you can replace coordinate geometry and complex analysis and matrix algebra. Pretty much everything else that you would need can also be done in geometric algebra. So Lie groups, that actual rotation thing I did, that element there is an element of a Lie group. It's very easily, they're all very easily expressed in geometric algebra. These things like spinors that come in quantum computing, qubits, they all fall out naturally from this fact that the Pauli algebra is just the same as the algebra 3D space. Quaternions we've already found. Differential forms, they're just a wedge. Grassmann algebra, that's just things that anti-commute. It's all there. Even obscure things like the octonions all just sort of drop out naturally. As does all of calculus, and all of Dirac theory, and all of quantum field theory, and gravity. And the person who actually put all this together, who sort of realized that geometric algebra was the unifying language of maths, is this guy, David Hestenes, who is a retired professor out at Arizona State. And he was the first person to realize that all of these things could be formalized inside geometric algebra. So I kind of think of it as a organizing principle for a lot of mathematics in the same way that I'm kind of attracted to functional programming as a higher level organized way of organizing your thoughts about what programming should be. And that's all part of the way I kind of see the two sort of meshing together very, very naturally. So just to finish up, the code that I've used there is on GitHub. As I say, it's my code. It hasn't been looked at by professionals. I'm very keen to see if there's anyone interested in the Haskell community who'd actually like to work on making this more robust, more professional, better optimized, better libraries, and so on, and building it up into a set of tools where actually you can expose all of those different types of area in the previous slide. The lecture notes will go onto this side, which is one I maintain at Cambridge, and that's where you can find lecture notes of all the other courses on geometric algebra. If you want to contact me, contact details there. If you're really interested, I think this book is still available in print. I've been warned that the EPUB version of this, they might have screwed up when they created it. I haven't got the bottom of that. So if you've got any issues with getting hold of it, just let me know and I'll see if I can find a copy. So that's what I wanted to say. I hope I've done a good job of convincing you that this is an interesting area. I hope I've shown you that if you play around with these tools, it's very, very easy to get into geometric algebra. It isn't some vastly complicated thing. It is just essentially counting swaps and being organized. It's not that difficult at all. But it does unlock a vast array of sort of new maths if you're sort of interested in looking at it. Okay, thank you.
We have a few minutes for questions.
Okay.
So we have addition and multiplication. Does it make sense to define exponential function on multi-vectors like we have exponential function for matrices using formal power series?
Yep, yeah, absolutely. In fact, that's the link here. So the rotor, the thing that did a rotation is a scalar and a bivector. You can also write it as the exponential of a bivector. And that's how you generalize e to the I theta to arbitrary dimension. So it generalizes complex numbers naturally. And the exponential is defined as a power series, as the same way we do it in writing e to the I theta as cos theta plus I sine theta. So all those algebraic things generalize in the obvious way. And we can divide by vectors as well. And that may not seem like much, but when you're coming to problems in differential geometry, the fact that you have a differential operator which has this vector property means it has a unique inverse, whereas a separate divergence and curl don't. And that gives you a powerful new technique you can use in solving problems.
Thank you. Do we have any more questions?
Has this been combined with non-standard methods like infinitesimals and so on?
Oh, good question. I'm not sure. I know there was a guy in Kent who did his PhD thesis on infinite dimensional geometric algebra, and he was looking at this. I'm not. Let me think. It's been used heavily in supersymmetry, and as you go into higher dimensional space with mixed signature, you naturally get things that square to 0, and they often play the role of infinitesimals. I'm not sure if it's been combined with non-standard analysis, but I don't think there'd be much to do there, because that purely tells you about the coefficients. It doesn't tell you about the actual algebra. But there may be something left to do. Well, there's bound to be something left to do there. There's always something left to do.
Hi. Has anyone tried teaching this to people before they learn vectors and complex numbers?
Yes. So my long-time colleague, Anthony Lazenby, who I wrote the book with, he taught geometric algebra to his 6-year-old son. And he once went to a conference where someone was showing off their Maple implementation of this. So it was being presented as a tool for researchers to study geometric algebra. And Anthony, he's a physicist, social things don't always come quite straightforward. He just went straight up to the guy and said, "Oh, that's really interesting. My 6-year-old son would love that."
Do we have any more questions?
Why isn't it really caught on? I mean, it seems to solve all known problems.
Well,
but if you pick up, if you pick up even a recent book on like general relativity, they even stick to the old, horrible indices notation for tensors.
This is the other thing it has in common with Haskell. and perhaps why there's a natural sort of match between the two communities. Yeah. It's clearly better, but it was discovered later. And Haskell is clearly better than C or C++, but it came later. It's very hard to replace entrenched views, particularly when the entrenched tools are good enough. And a lot of practicing physicists, they learn the maths at school. They don't care too much about the techniques. They care about the results they get. And a lot of coders don't care too much about how good their code is, as long as it compiles and they get paid.
You gave an example of processing very high-dimensional vectors. Why would you want to do that?
So just a sort of simple example, it's a lot of the interest in geometric algebra now is in 5-dimensional space with mixed signature, because that gives you a representation of the 3D world where rotations and translations and inversions are all linearized. So there are various operations that get linearized, that are nonlinear in 3-dimensional space, that become linear in higher dimensional space, like projective geometry and so on. One of the other reasons is just pure mathematical ones. This is a really nice way of studying group theory, But there are lots of interesting groups out there in very, very large dimensional spaces. And I kind of use this as a tool for exploring them. So at that point, you need these big spaces. If the string theorists are to be believed, which they're not, but if they are to be believed, then we would need to be doing calculations in 26 dimensions as well.
Do we have any more questions? No? Right, well, thank you very much, Chris.
Okay.